Earth is in danger. Scientists are a step away from creating a black hole, a scientific experiment that could lead to the apocalypse. Articles with similar headlines began surfacing in the press in the early 2000s. The Large Hadron Collider, or simply LHC, started up in 2008. It caused a real storm of discussion. While some scientists planned grandiose experiments, others warned mankind of serious danger. How does the LHC work, and is it really capable of destroying our planet? The Large Hadron Collider is installed underground near the French-Swiss border. It's a ring-shaped tunnel with a circumference of 27 kilometers or 16.7 miles. Two vacuum pipes are installed inside the tunnel, which intersect in some places. 1,232 main magnets are connected to the pipes. Their task is to accelerate protons to a speed close to the speed of light, and then hold this stream so that the particle beams don't crash into the wall. In order for the magnets to work, they're powered by superconductive cables with a total length of about 250,000 kilometers, or about 155,000 miles. If scientists got tired of the LHC and they decided to dismantle it, these wires could be wrapped around the Earth about 6 times at the equator. And even after that, there'd be enough wire left to run a power grid somewhere in Antarctica. Although, why a power grid in Antarctica? Well, they aren't planning to disassemble the LHC yet. However, it could be considered the largest refrigerator ever created. For proper operation, the collider magnets need to be cooled to minus 271.3 Celsius. That's minus 456.3 Fahrenheit. That is, to create a temperature lower than in space. To get this cold, 120 tons of liquid helium is poured into the LHC. Now, look at the refrigerator in your home. In it, there are special substances, refrigerants, that create cold. Liquid helium is one of them. In one household refrigerator, there are approximately 30 to 50 grams, or 1.05 to 1.76 ounces of refrigerants. So, we can say that the LHC surpasses this indicator by approximately 4 million refrigerators. Only instead of cooling products, it helps solve the most complex problems of modern physics. For example, what does matter consist of? From school, we know that matter consists of molecules of atoms, and atoms of protons, electrons, and neutrons. But modern science has gone even further. It turns out that even the smallest particles of the atomic nucleus, for example protons, consist of even smaller particles, quarks. Want to know how small they are? Then imagine that an atom has grown to the size of the Earth. Then a proton would have a radius of about 100 meters, or 328 feet. That's almost the length of a football field. In this case, the quark would have a radius of about 5 centimeters, or 2 inches. That is, it could fit in your pocket. But how can we examine such small particles? This is why the LHC was created. You take 2 beams of protons, accelerate them in opposite directions, and collide them with each other. What would happen if you put a brick on the ground and threw another one on top of it? Most likely, small fragments would fly off in different directions. Similarly, when protons collide, tiny particles can break away from them. In ordinary language, a collider is needed in order to see what happens when the protons and heavy lead nuclei collide. As the creators of the project admitted, pushing 2 protons together is about as difficult as getting a needle into a needle, provided that the distance between them is 10 kilometers or 6.2 miles. And at the same time, they need to collide exactly in the middle. Not so easy. In addition, these small particles are invisible, so physicists can only study them by examining the tracks they leave in their wake. Another task of the LHC is to find something new. It was with its help that the Higgs boson was discovered. This invisible particle can be called the foundation of the universe. After all, it's this particle that gives the other ones, and therefore all matter, mass. It turns out that if it disappeared, all particles would become absolutely weightless and fly around the universe at the speed of light. In addition, with the help of the LHC, it's possible to study other elementary particles. Each of them helps in the emergence and interaction between atoms. And each of these particles is so small that they can be detected only when proton fluxes collide. Scientists register the particles that are then formed with the help of special detectors. Another interesting area of research is antimatter. In our world, atomic nuclei have a positive electric charge. Negatively charged electrons revolve around them. But for each particle of an atom, you can create a double, an antiparticle. It has the same mass and properties, but the opposite charge. For example, an electron is negatively charged, and its antiparticle, positron, has the same mass but is positively charged. The same goes for protons. Protons are located in the nucleus of an atom and have a positive electric charge, but their antiparticles, antiprotons, carry a negative charge and at the same time have the same mass. We can say that antiparticles are a mirror image of ordinary particles. If you approach a mirror, you'll see your reflection in it. If you wave to it with your left hand, your mirror double will answer you with a wave of its right. Antimatter is similarly arranged. With the help of the LHC, it's possible to not only create antiparticles, they can also be combined with each other to create whole atoms of antimatter. Under ordinary conditions, when one proton and one electron are joined, a hydrogen atom appears. Now, we can take two antiparticles opposite to the proton and electron, the antiproton and positron. Connecting them, we get an antihydrogen atom. It will have the same properties as hydrogen itself, but only when antihydrogen collides with an ordinary atom would an explosion occur. A strong explosion, as a result of which an incredible amount of energy would be released. 1 kilogram, or 2.2 pounds of antihydrogen, can produce slightly less energy than was released during the Tsar Bomba explosion. And that was the most powerful of all hydrogen bombs ever created by mankind. Most physicists believe the LHC is pretty cool. There's only one small problem. It's believed that one of its future experiments could destroy our planet, or at least it could create serious problems. In 2008, opponents of the collider, Walter Wagner and Luis Sancho, even went to court. They demanded a prohibition on starting up the LHC. The applicants feared that if protons collided so strongly, they could form a microscopic black hole. The gravity of this object would be so great that it would immediately begin attracting the surrounding molecules, or it might completely drag the entire Earth into it. But don't worry, none of the past experiments have confirmed the possibility of creating black holes. Even if such objects appeared inside the tunnel, their size would be so small that they would evaporate instantly. So the lawsuit to ban the LHC was rejected by the court. The LHC started up, and so far it's been working successfully. There's another potential threat. Scientists believe that in some places of the universe there are wormholes. These are hypothetical objects in which space-time is curved. We can say that these are tunnels connecting two remote areas of space-time. And if you enter one of these tunnels, you could either travel in time or instantly move somewhere very far away, even to another universe. Some scientists fear that high energies may create such a wormhole inside the LHC itself. However, this is just a theory. The creators of the LHC claim that such particle collisions occur on our planet even without human intervention. It's believed that for billions of years, various cosmic particles with an energy millions of times greater than the energy of protons in an accelerator have been bombarding the Earth. And this hasn't led to the appearance of black holes on the planet or other terrible consequences. It's unlikely that such an experiment inside the LHC would transport us to another dimension. But moreover, I'm carefully monitoring everything that happens with it. So if anything ever goes wrong, you'll be the first to know about it. Don't forget to subscribe to the channel to follow along with me on future experiments. And be sure to like this video and share it with your friends if you haven't done so already.